So to do this, we know right here that how fast this thing was going off the bat. So we know this part of the triangle right here, 3,066.88. We know that. And we know that the angle right here is 45 degrees. We're going to call this our y component. We're going to call this our x component. Now we're going to get into some trigonometry to solve this. So to do this, all we got to do, if you're solving for v of x, which is the velocity of the x, this is the v of t in the horizontal direction. This is what it means. So to do this, all you got to do is take cosine of 45, or pi over 4, and multiply that by 3,600.88. This right here will give you the velocity in the x direction. So that will give you, when you do it, 2,546.21 meters per second. So this number right here is this number right here. This is what it is. This is what it's equivalent to. So this is how fast this refrigerator with Indiana Jones is moving when it's going horizontally across the ground. So if it had no air, no angle, nothing, that's how fast it would be traveling. Now, to do this problem, we need to find out the y value too. So the y value is how fast it's going in the upwards direction. So with this initial velocity, this is how fast it would be going. You shot it straight up. So to do that, we're going to do the same thing. We're going to set v of y. In this case, v of y is the velocity in the y direction, just like I explained, in the upwards direction. So to do this, we're going to do straight once again. We're going to do sine of pi over 4, which is 45 degrees, but degrees in calculus don't mix, so we're going to use radians. And then we're going to multiply, same thing, 3,600.88 meters per second. And when you do this, you get 2,545.58 meters per second. This right here is your vertical. This is how fast Indiana Jones is moving in the upward direction. This right here is how fast Indiana Jones is moving in the horizontal direction. Now, this is where we can use these things. This is where they become helpful. So we know, I'll explain in just a minute. You learned in calculus that the average velocity, or the average acceleration when you're going up and down is 9.8 meters per second. You can solve for this using integrals, derivatives, you name it. You can figure this out. So in this one, we're going to assume that gravity in the y direction has an acceleration of negative 9.8 meters per second, because it would be falling or rising in that direction. So to do that, what we're going to do is we're going to do, once again, this basic equation. So we're going to do v final on the y, which v final on the y is saying when we launch this thing, at rest at the end, how fast is it going? That question can be answered because you know that when this thing is all said and done and it's resting in its final position, you know that the velocity, it's obviously not going up anymore, so you know that is 0. And then we know, because we solved for it right here, that the initial velocity of this thing in the y direction going up and down, because we're talking in the vertical direction here, we know that this is the value for v initial. So I'm just going to write the equation first. So this is the v initial and the y. This is all discussing v of t. V of t. This is a calculus symbol that everyone should know. We're using v of t. And we can do with this, it's at the end of the equation, the acceleration and the time. Now, what we're going to solve for here is we're going to try to find out how far this thing went until this point right here. Because this is where you know that the v final, when it was all the way up, this is when it stopped its upward direction and went back down. So this is how you know the final velocity in the y right here is 0. And you know, because you solve for it, that the velocity in the vertical direction is 2,545.58 meters per second. So you know that value. 5.8. Plus, what I just described with the acceleration in the vertical direction, is negative 9.8 meters per second squared. That's what we're going to use for our acceleration. And then that's multiplied by time. Now, what we're solving for, I'll mention again, is we're solving for how long this thing takes to get from the beginning, right here, to this point right here. That's what we're trying to solve for. So that's how we know how far it went. So to solve this basic equation, subtract from both sides, 2,545.58, and that would equal negative 9.8 t. So just divide it out, you get your time, equals 259.75 seconds. This is how long it takes to get from the beginning to the top of its peak when it's launched into the air. Now, to get the whole time from here all the way to the end point, all you gotta do is multiply by 2, because this area right here is the same as this area right here. It goes up to its point, goes down from the point at the top. So all we gotta do is multiply this number by 2. So we want 2t, so 2t equals 519.5 seconds. That's how long this refrigerator with Indiana Jones would be in the air with a nuclear force explosion, with the amount of weight that he's carrying with the fridge. That's how that would happen. Now that we've solved for time, we can figure out how far this refrigerator with Indiana Jones went along the ground. How far is this distance? That was our question in the beginning, because this is where we're going to find out how realistic this truly is with a nuclear explosion. So, to start this, we're going to get rid of this because it doesn't really pertain anymore. Now I'm going to introduce a new equation, because this is what we need to do to solve it. So this is the equation right here. Okay, so this is what we need to do. This is the equation. So x right here, your x of t. This is another calculus symbol that's very important that all you should know. X of t right there, that's distance just like it always is. This is what it is. And this right here, x naught, so this is x initial. So your initial distance, this is what that is. And I'm going to describe it as how far did this thing go when it's sitting right here. Obviously it hasn't moved at all, nothing's touched it. The x naught right here equals 0. Obviously, that's what it is. And your initial velocity, that's what you want to find out. How fast is it going when it's sitting here? Once again, it's not doing anything. So the time here doesn't matter. So that value right here also equals 0, because it just isn't part of the equation, and it doesn't matter in this case. So you're going to get your distance equals 1/2, your acceleration, and your time squared. So at the beginning of the problem I talked about how fast is this thing accelerating when it happened. That's what I wanted to talk about. So to do this, all we got to do is take that initial value that I had, which was the initial acceleration, so this is also another calculus term, a of t is your acceleration. That's what I have, and this is what you need for this problem. So your a of t, or acceleration, when you do this, you get 1/2. At the beginning of the problem, I stated it was 72,017.68. That's the acceleration. Now, you also know the time, because we solved for it right here. You know how long this thing would be in the air. That's, you know. So it would be 519.5 seconds. All this is with the force, and it would also be squared. So that's how fast, this is right here, how far it would go. Now, if you plug this into your calculator, you get an insane number. You get 9,178,074,741 meters. That is an insane number. And I'll tell you why it's an insane number right now. Because all this physics, all this math I just did, was that I took a big 200 kilomegaton nuclear explosion and I put it to 1 point. If I took all that power of it and I put it to 1 point, right here. So all the power of a nuclear explosion right here, big plume going out in its outer directions, and I put it right on this point. That's what I just did. To make it more realistic, because all this is done if nothing got in its way. I'm explaining this like if it was just an easy